Hello and welcome to the second TCIPG webinar of the year. Today we are pleased to have a TCIPG alum, graduate who got his doctorate here, Salman Zunuz, who's now at the University of Miami. And it's a good time for him to be here in early February because, of course, in central Illinois, we have spring this time of year. And the buds are out and the birds are singing. No, just kidding. It's actually below zero, and Salman forgot his gloves. So he may have a little difficulty advancing the clicker. Anyway, so as I mentioned, Salman is a graduate from here, and he is now an assistant professor at the University of Miami, and also runs the 4N6 Center, which is a research center in cybersecurity with a number of faculty and PhD students. Today he's going to be talking about a trusted verifier for code in controllers. Without any further ado, I'll just turn it over to Salman. Thank you for coming.
Thanks, Al, for the introduction. Actually, it's great to be back home, especially cold home. So today, and thanks for coming, actually, for the presentation. So today I'll be talking about our solution TSV, Trusted Safety Verifier for cyber physical control systems. But first, I'd like to really appreciate as a collaborative effort, I'd like to appreciate our collaborators, specifically our research group members, the forensics, Henry and Alessio, Penn State University, Steve, Devin, and Patrick, and our long and great collaboration with the University of Illinois. Both while I was a PhD student here and after I graduated, Rakesh, Tim, Robin, Ed, Pete, Tom, and Bill, and our firewalls collaborators, Kate and Matt, that we've had great long collaboration with. So today I'll be talking a bit about the background material on smart grid infrastructures and what threats are potential threats against those cyber physical infrastructures, and our solution against to defend against one of those threats, TSV, Trusted Safety Verifier, and finally I'll conclude the talk. So in very high level, from a high level viewpoint, the power grid includes the power sources where the power is generated, and then we have transmission network to transfer that generated power to distribution network, which is in charge of distributing the generated power among the end users, the household owners, for example. From a bit of more technical viewpoint, we have those three generation, transmission, and distribution segments shown here on the power world snapshot. And particularly, for example, if we have the power system buses where the power system components meet each other, we have the power generators where the power gets generated. And we have the load, which represents the end consumers that consume that generated power, which is being transferred over these transmission lines shown on the diagram. So this is the traditional power grid. But when we talk about smart grid infrastructure, that is where we talk about smart monitoring and control of the grid using intelligent cyber infrastructure. We talked about monitoring and control, and that is mainly done in power control network that also needs to get smarter for smart grid applications. And this well-known but kind of complicated diagram of the power control network shows different pieces of a typical power control network. Specifically, we focus on the top part, which is the control system network or control network. In particular, I'd like to highlight some components there, which we will concentrate on today. The HMI server there, the human machine interface servers, that kind of are those big monitors that you may have seen in power control centers that power operators look and they visualize the underlying power system, and then they use that to monitor what's going on in the underlying physical system and take control actions. We have at the field, at the substation levels, we have devices like RTUs, or specifically, I'd like to point out the PLC, like programmable logic controller, that are used for control automation, and they are out in the field, but they talk to HMI servers. And we have data acquisition servers that are dealing with measurements and sensor information coming from SCADA, and also PLC and RTU devices. We have security solutions deploying the power control networks like firewalls, as well as security sensors like intrusion detection systems, both host-based and network-based, deployed there to monitor what's going on, if anything malicious going on, to alert, to notify the operators or security administrators of the network. So we talked about the smart monitoring and control of the system in a very high level. What that means when we talk about monitoring, we're talking about observing and sensing the underlying physical system using different sensors. We have current transformers, power voltage transformers, PMUs or phasor measurement units, etc., other SCADA sensors, and these measurements come in. They are both could be and are often noisy, and also these sensors are not monitoring every point of the power grid. So we need state estimation. What the state estimation problem is that you get these noisy measurements, incomplete measurements from different parts of the system, and you want to see what the state your system is. And the state vector mathematically is basically voltage phasor of each bus on the system. And you get these noisy measurements, you get your system topology, which is represented by these power flow equations that is shown here, and you come up with the state vector that fits those measurements the best. Now that you know what the state your system is, you can control the underlying power grid. And by control, you can take different actions to open, for example, open close a relay or set a generation set point, or send a controller command to the PLCs. Again, programmable logic controllers, that will be the focus of our talk today. So looking at the such a cyber-physical system, let's look at what threats are there and some of the solutions that we've worked on in the past. So we have at the top part the control center, the cyber part of the power grid, and the underlying we have the power system, the physical part of it. We have different sensors on the left that sense different aspects of the system. They send measurements to the control center, and the control center comes up with some control actions, sends them back to the power system actuators, which are in charge of controlling the system. So looking at the threat, where can threat be? First place that threat could be in is on the sensors. So the sensors could be corrupted. As one solution that we worked on ITRON smart meters and design intrusion detection system for specifically detecting energy theft attempts, using different sensor information coming from firmware sensors on the meter, as well as the physical anti-tilting, for example, sensors, as well as NILM approaches, like non-intrusive load monitoring approaches, to figure out if a particular household is trying to steal some energy. Another sensor-based defense that we've worked on was to design actually that chip there, which is basically a current transformer, a sensor that would encrypt the AC signal or analog signal right at the data acquisition point. And for that, we use digital potentiometers and microcontrollers. And the point of encrypting or encoding the AC signal right at the data acquisition point is that your measurements, which are going to the PMU, is already encrypted. So even if your PMU gets compromised by the attackers, you're safe because your measurements are already encoded. Your measurements could be corrupted by attackers, so-called false data injection attacks. And there's a lot of solutions proposed for that. Our solution used a combinatorial approach, which basically means accurate, but we made it also scalable using extra information that comes from the cyber side, in addition to the physical side power sensors measurements. We also use the cyber side intrusion detection system alerts to kind of reduce our search space. On the control side, when it gets attacked, the first question that needs to be answered accurately is what state my system is in. Right now, I'm seeing like some abnormal behaviors in the system. I want to see which host computers in my system are compromised and which ones are not. And for that matter, we basically propose FlowGuard, which is to use to make an efficient use of different sensors by deploying them on demand because they come with performance overhead. So at this point, we have the knowledge about what state we are in. We want to see, okay, now I know what state I'm in. I know which computers are compromised. I want to see how secure is this. Am I very secure? Am I just completely insecure? Or the security is kind of fairly okay? So for that matter, we designed SecList, which was a security metric using the information flow analysis between assets like files and processes, so that even if your state estimation server, for example, is not compromised, but something else that the state estimation depends on is compromised, then you get a good sense of how likely is that your state estimation does not give good results. So at this point, we know what the state we are in and how secure each state of the system is. In our recently published paper, we worked on SOCA to explore potential next states of the system that attacker could potentially drive our system towards. So right now, I know like what the state I'm in, how secure each state of the system is, and I know what potential next states the attacker may drive me towards. So now I can take some automated actions. That is where the RRE solution that we've worked on comes into play. So to take automated response actions to proactively prevent the attackers from driving us towards very insecure states of the system. In a follow-up work that is also, we're still working on it, on Element, we try to make this automated response that required a lot of power, basically human involvement, to define cost functions that are used for optimal response action selection procedures. We try to learn those cost functions automatically by just passively observing the power operators, how they deal with security incidents when they happen, so that we learn these cost functions, and later on in the power operator's absence, we use the same cost functions to kind of imitate their action, response action, if the same or similar security incidents happen. And finally, the threat could be on the control commands. The attacker could inject control commands before sending to the actuators, like the PLC devices. That is going to be our focus today. The TSV work, Trusted Safety Verifier. So as an example of an attack against such PLC, not specifically on the power system, but in a cyber-physical infrastructure, the nuclear power plant was a Stuxnet. So what the Stuxnet did was, through a lot of attack vectors, it compromised the HMI server. And once the HMI server is compromised, they modified the DLL library files of the Step 7, which is the controller software by Siemens to control to interact their programmable logic controllers, to inject a malicious code. So whenever the HMI server would like to, basically the power operator would like to upload a controller logic program on the PLC for execution, Stuxnet would intercept it and inject its own malicious controller program for execution on the PLC. So what ends up happening is that the malicious code runs on the PLC and the underlying physical system goes unsafe. So what the Stuxnet did, or did really well, was on the cyber side. It used a lot of attack vectors to compromise the HMI server, but what it did not really do well, basically how it did on the cyber physical side was to have this malicious controller program pre-compiled, included in its own executable. So it was literally a targeted attack. Which means attackers already knew about exact infrastructure configuration of the target machines or of the target infrastructure. But on the cyber side, we see malware now coming up, which are more adaptive. They don't know upfront what's going on, but they kind of literally do reconnaissance and then change their behavior. So is that a possibility to attack that we'll see? The answer is yes. But before getting to that kind of demo video, let's look at what a PLC is. I've been talking about the PLC, programmable logic controller, but what is a PLC? It's a MIMO, multiple input, multiple output digital reprogrammable controller, which has three main portions. Basically, it's a kind of simple device. It has input modules that gets input values from the input wires that are coming from sensors. Then it's got CPU that executes the controller program uploaded by the HMI server. That PLC executes that controller program to process those input wire values, and then comes up with output wire values and just writes them to the output wires that are connected to the actuators to the physical system, to control the underlying physical system. And it's used like widely in industrial control automation and for substation interlocking and load management and so on and so forth. They have simple programmable languages. They have, for example, the graphical ladder logic that you see at the bottom right, one example of it. It's a kind of graphical language. Programmable language like function blocks or instructional list language that I'll be talking about later today. They are hard real-time systems, so the outputs should come out within a hard deadline, so within a bounded time interval. And finally, it is also very crucial to understand how PLCs execute for our talk today. The cyclic I/O scan cycle, they have like a cyclic I/O scan cycles, which means I talked about how input, output, and processing or CPU modules interact. But the way CPUs actually work is that they start by just taking a snapshot at once of all the input wire values. So all those input values are taken a snapshot of, and then they are processed during the scan cycle, which varies between 10 milliseconds to 150 milliseconds. But it's fixed. Let's say it's 10 milliseconds. So during that 10 milliseconds, those input wire values that have been taken up front at one time are processed by the CPU, and at the end of 10 milliseconds, or the scan cycle, all those output values that are computed now are written to those output wires at once again, okay? So, and the next step is basically to do the same thing periodic. So they go again back to the input wires, take a snapshot, process, and write to the output wires during the second scan cycle. So what this means is that during the scan cycle, basically while CPU is processing those values, if the input wire value changes, it does not affect the execution because their value has already been taken a snapshot of up front. So I talked about Stuxnet, how it had a fixed precompiled executable on the PLC. What we tried to kind of play with this attack was whether or not it's possible to, rather than having everything prefixed, to just update the execution or the controller program on the PLC, rather than having everything prefixed and loading an entirely new executable on the PLC. So before getting to the actual demo, let's look at different compartment or portions of the PLC that I just talked about. So this shows an actual PLC, and we have the CPU that processes and runs the controller logic. Below that, we have the input modules, and at the bottom, we have the outputs. So the input modules could be analog or digital, as well as the output modules. And in particular here, we can see that that only input module is on, and the rest LEDs or input wires are off. And the output side, only those two are on. These are digital output wire, again, modules. And the rest LEDs or output wires are off. So those are, again, connected to actuators, or could be. So looking at this demo here, so this kind of shows a potential malware against cyber-physical systems that we will present how TSP would detect or stop such attacks from happening. So in particular, we have this attack machine here, which is a Linux machine, and we have the HMI server that is connected to the PLC. In particular, we didn't really focus on the cyber side of attack because Stuxnet had done a very good job already on that part, and we mostly focused on the cyber physical aspect of it, on this PLC part of it. So we just used a Metasploit to compromise the HMI server that is connected to the PLC here. Again, the point of this demo is to show whether it's possible to modify the execution or the controller program running on the PLC. So that, because PLC could have a lot of output wires. In that particular case, we had 32 output wires. And as a malware, you probably know just one output wire, and you want to change that one, not the other ones. Why? Because you want to go undetected. It's a physical world. So any consequence, it is much simpler to detect than in cyber world, where you, for example, your consequence could be a file deletion, and you wouldn't notice it unless you have a very security sensor watching for it. Okay, right now what happens is like it's got a TCP reverse connection to the HMI server, and it's trying to upload the malware on the HMI for execution. For demonstration purposes, we are doing everything here step by step and just showing it, but of course everything could be just scripted in an automated fashion. So here we're just, as I said, uploading the malware. At the next step of the attack will be on the HMI server right here. On the right, you see the running PLC device, and on the left, you see the HMI server, which is connected to the PLC. The Stuxnet assumed that the HMI server is running a step 7, which is a fairly large software base by Siemens to control or interface the PLC devices. Our attack does not have that assumption. So we connect the PLC using the libnodave library, and then we have, in our lab, developed disassembler and assembler for the PLC device. So we connect to PLC with no step 7. We fetch the running executable binary format, which is MC7 or machine code, from the running PLC. It just downloads it from PLC. And next step will be to, this is machine code, binary code. We will disassemble it. So we will get the source code of the controller program, which is in STL programming language or ILIL instruction list programming language, which looks like an assembly language, but they are different. And we just downloaded the main organization block, or let's say the execution portion of the PLC, which is OB1, or organization block 1, that periodic or cyclic execution. It includes the code for that cyclic scan cycle execution. As I said, we just disassembled that executable. And once we disassemble that executable here, as I said, everything could be just automatically done by the malware. Once we have the source code of the running controller on the PLC, the malware could, rather than having everything prefixed and compiled in itself, would just inject a malicious instruction to that executable, to that source code, recompile it without any connection back to the attacker, and would upload it on the PLC for execution. So right now, as we see, like we have just one input wire on, which is because of this incoming wire, and two outputs on only, which could potentially be connected to the actuators. Now we're going to go ahead and basically launch the attack. Okay, we launched a full attack at this point. And several steps. First, to connect to PLC. The second step will be, again, to fetch the running control, the executable on the PLC. Next, we're going to disassemble it. And this part is basically done in a scripted fashion. And now we inject a malicious instruction in that source code before compiling that source code back to the MC7 machine code format for execution on the PLC. And then just send it over. Again, just take a look at the underlying output wires. We have two on, and right now we got the third one on without affecting the other output wires that could be controlling some actuators. As I said, why? Because the attacker may just have or the malware may have just partial information about the infrastructure, does not want to mess up with other outputs to go undetected for a long time. And finally, I'll just probably skip ahead, and the modified controller that is now running on the PLC has just that last injected instruction by the attacker that caused this extra output wires to turn on. And that particular instruction is just, I'm going to show that modified instruction, which is basically to set Q2.5. It's just updating that particular output wires, which is kind of exactly what I wanted to say. So we have such attack feasible OK. So given that attack, now our solution tries to kind of defend against such attacks. We'll see how. What is given right now is a controller. Imagine you're sitting between the HMI server and the PLC device, and the code is being requested for execution on the PLC. So what we are given with is a controller code for execution on the PLC. And imagine we are also given with the safety requirements for the infrastructure, for the physical infrastructure. So if you are in a power operator, for example, and you have a PLC controlling a generator, and you know that that generation set point cannot go beyond the predefined threshold, so your safety requirement will be the generation set point that could be set by this PLC cannot be above that threshold. That is simply your safety requirement. Formally, that safety requirement is going to be stated in a linear temporal logic, which is propositional logic plus some temporal operators that we'll see about in a minute, actually later in the talk. And the goal is to design a minimal TCB or trusted computing base to detect whether that executable that is now requested for execution on the PLC could potentially be a malware. More formally, could that violate my safety requirements of the infrastructure? TSVR solution is just shown here. On the left, you have the power operator looking at the HMI server and is running the HMI server to upload the controller program for execution on the PLC, shown on the right. In the middle, we have our solution TSV, which is running on a Raspberry Pi chip and as a bump-in-the-wire solution. And wherever the HMI server is going to upload or request for an execution, the controller program upload on the PLC, TSV would intercept that call, get that program or executable, would disassemble it, and analyze it and see if that could violate those safety requirements of the infrastructure or not. If it basically cannot or could not under any circumstance, it just will let it pass through for execution on the PLC. Otherwise, it will come up with counterexamples or safety requirements violating input vectors and send the actual executable or the program back to the operator along with those input vectors so that the operator can now debug or say, oh, this is not the executable which I requested to be sent for execution on the PLC, which was the case in the Stuxnet. So in particular, what that analysis means is in high-level analysis of the code, is that we get that executable, disassemble it, create a model of that program, the controller program. And then we will just run model checking solutions to figure out if that program model could violate my safety requirements or not. But the first step of that analysis is to, once we disassemble it, we have the source code. But those source codes are really hard to analyze, so we have to translate it into an intermediate level language that we call it ILIL, so that we have a common base for analysis. We'll see in a minute why actually we need that. So this is the programming instruction list, is the programming language that the operators use to write a controller program for execution on the PLC. And they are like, as I said, as we see on the top right, they look like an assembly language program, but they are different. Specifically, kind of particular things about them is that they have function blocks, which are like functions, but not quite, because they don't have a stack, they don't have relative stack pointer addressing. Everything is in an absolute address space. They have hardware timers that could be set. They have counters so that you can, for example, count number of times. For example, an input wire goes high from low, from 0 to 1. And something to notice here is that these counter values are stateful values. I talked about the scan cycles, periodic scan cycles execution on the PLC. These counters remain their value. They are stateful variables so that they are not reset across the scan cycles. That will be important for our formal verification procedures. Master control relays that are basically emergency reset inputs. The data blocks are persistent data storage that are used for different purposes. For example, the function argument passing. There are several instructions on the instruction list language that that act on an basically edge detection basis. So they act if your input goes from low to high only. More particular features of this instruction list they have is that they lack a high-level language. I'm not talking about C or C++ or Java here. I'm talking about instruction list that looks like an assembly. So if you want to analyze it, we kind of end up doing some binary analysis. They have particular type of addressing. For example, they have hierarchical addressing, so that rather than having a fixed address, like we have 32-bit address in x86 executables, here we have some namespace qualifiers before that address space. And Siemens, for example, PLCs have one of them. Allen Bradley, for Siemens, it's the memory area. Allen Bradley has 3 of them. That prefixes comes before the actual address. And address itself also is multi-indexed memory addressing. Basically, it follows that scheme. What does multi-indexing mean is that, for example, in x86 executables, we just, for example, could address 1 byte. Here, we can address 1 byte, 1 bit, or 1 word. So it's kind of, so our formal verification should take care of all these features of the PLC programs. So we have that programming language, but why do we need an intermediate level language, or ILIL as we call it? It's because the direct analysis of this programming language or instruction list language that power operators use to write controller programs for PLCs is difficult. Why? Because of its implicit control flows. What do I mean by that? In x86, like just in an analogy, at the end of basic blocks, we have compare registers, and then it sets some flag registers, and later on we're going to say jump, and there's an implicit check whether that flag register has already been set. So those implicit control flows, we have to make them explicit. So that's why we need an intermediate language that we call ILIL to make all the control flow explicit. It will increase our code size significantly, but at least it's going to be much, much easier to analyze. Second reason for the need to this ILIL programming language is that IL, or instruction list, the programming language for PLC, differs slightly across vendors. So we need a common base for our analysis. And on the right, you see the grammar for our ILIL language that I won't get into its details, but the details are all in the paper. So I already talked about all these like points here, but just as an example, we see on the top a simple instruction list program. The first line says and input wire I, first byte 0, fifth bit 5, and it. So it means if it is 1, then make my Q, which is the output wire, first byte 0.1, the first bit 1. So if my fifth bit of input wires is 1, my second bit of output wires will get 1 as well. That goes to the actuator. But that it's translated version of ILIL, now that every control flow is kind of explicit, you see like how the code size increases. But we're going to analyze now the ILIL program here. Now that we're done with that, the first step to analyze this translated ILIL program is to run a symbolic execution on top of it. But what's a symbolic execution? Just a very brief review here. Let's imagine we have the pseudo code. We have a first line, we have an input I, we have an output O, and then we read I, and we say if I is less than 10, my output is going to be I plus 9, else my output will be I over 2. Right? The same code segment could be represented by this control flow graph. That basically, it has those boxes are called basic blocks, and it's the same source code, and the branch there is caused by that if condition. So if I is less than 10, we go left. If I is larger than or equal to 10, we go right branch. Now, when we talk about execution, We usually, when we execute the code, we all know that concrete execution, we give concrete values. My inputs are, if it's an integer, my input is either 1, 2, 3, or 16 here. And then I go through the code and say, OK, my input is not less than 10, so my output will be input over 2. So that becomes output, that makes the output 8. But when I talk about symbolic execution, rather than concrete values, my inputs get symbols. Like, for example, my input becomes A. Then the output, what I do for during symbolic execution, I'll take a look at the control flow graph of my source code, and I'll just exhaustively try to explore all possible paths in my code. And then the output will be a mapping between so-called path conditions, which are, in this case, just that if condition there, and the symbolic output values. So if I, for example, go the left path, the path condition will be if my input, in this case symbolic A, is less than 10, my output will be symbolic value input plus 9, my I is A, so it will be A plus 9. And the second mapping is if my A is not less than 10, meaning larger or equal to 10, then my output will be I over 2. In this case, I is symbol A, then my output will be A over 2. So that kind of gives me all possible path output, even symbolically, of the execution of this code. So I'm going to just run the same symbolic execution on my translated ILIL program. So whatever path that I will go through this control flow graph of the ILIL program, I'll do just some satisfiability check. So if I, for example, end up in some path condition that we saw the mapping right here at the bottom of this blue box, the path condition A less than 10, if that path condition becomes X is less than 10 and X is larger than 20, I'm going to check some SMT solver, the satisfiability check engine, to see if this path is feasible. Is there any concrete value that will make this path explorable? In this case, of course, not. So the symbolic execution engine will just simply backtrack and go through the other path, just not to waste its time. A bit technical here. For symbolic execution of the ILIL program, we do bounded loop unfolding, which is kind of well known in programming language, the domain. But with the exception that here we're going to be guaranteed to be correct in the PLC world because of the scan cycle times. So scan cycle time, if it's 10 milliseconds, and I know my for loop, let's say, cannot execute more than 10,000 times within 10 milliseconds. So I just need to unfold this loop 10,000 times, and I'll just be guaranteed that my verification results will be correct at the end. I'll probably skip through those bullet points there, that we do some indirect function call resolution to be more scalable, and we do opcode-based register type inference without getting into details. But finally, after the symbolic execution, what we're going to have, what we just saw in the previous slide, that this mapping between path condition and output, symbolic outputs, we're going to have the same. We're going to have a mappings between path predicates or path conditions and symbolic output variable values. But something to notice here is that this is a single execution of that code. We talked about scan cycles. The PLC repeats every 10 milliseconds and runs the same code over and over again. The symbolic execution output does not consider that temporal dependencies across scan cycles. So we need to take care of that next, which is going to be done by what we so-called temporal execution graph. We have these symbolic execution outputs, these mappings between path conditions and symbolic output variable values, and we're going to just use that to generate a temporal execution graph that takes care of these inter-scan cycle dependencies of the PLC code execution. So right here, we see, again, a very simple code segment, pseudocode. We have input I, output O, an internal variable, a stateful variable like a counter, for example, that we just talked about, that doesn't get reset across the scan cycles, that just gets incremented every time this code executes. And then read input, and if I is less than 10, output will be I, or input, plus 9 plus that internal variable, stateful variable x, else output will be I over 2 plus x. So having the symbolic execution output values, I'm going to create a temporal execution graph that is shown at the bottom. My first state, basically each state is a set of symbolic variable values of that program, and edges between those directed edges between those states represents scan cycles. Okay, so the first node here, the initialization, I just set everything to 0. That is what happens when you turn on the PLC for the first time. If you give, and let's say it just gets an input again to that input wire that we saw on actual PLC, and for the first time execution of the code, I call that input I superindex 0. So if that input value is less than 10, I'm going to take the, I'm going to take the left edge. Now my x, which is the internal variable, has increased to 1 from 0. And my output has now a symbolic value from the symbolic execution output, the value of I superindex 0 plus 9 because of that if condition there. And my x was 0. Now, for the second scan cycle, when the PLC goes for the second scan cycle, it's going to rerun the same controller logic. Now my path predicate or path condition will accumulate. And in that state, at the bottom, I have x again incremented to 2, and my output will get another symbolic value. Right now, we have another I, which is the I superindex 1, which is the input wire value right before the second scan cycle, or second execution of the controller program on the PLC. So to generate this temporal execution graph, we do some optimizations. So again, we don't go through some paths here that are not feasible. So for example, looking at the edge at the bottom, I superindex 0 less than 10, and I superindex 1 less than 10. Do we have concrete values that would satisfy that condition? Yes. If my before first scan cycle, if my input wire is 5, and before second scan cycle, my input wire becomes 8, both of them are less than 10, so I can go through that path, so that is satisfiable. Otherwise, I will just not bother go through that path while I'm creating this TEG, or temporal execution graph. So we get rid of any intermediate variables within the temporal execution graph. What that means is that right there in the source code, we have output equals I plus 9 plus x in the if condition. But right here, when we calculate the values for the output value O, we get rid of all the x's. So for example, for the last state at the bottom, the output becomes I superindex 0 plus 9 plus I superindex 1 plus 9 plus 1, which was originally x, but we replaced that with its concrete value. And then we also, for more optimized TEG generation, we just minimize or simplify all the expressions mathematically. So simply just if we have the output wire value x plus 2 plus x plus 1, we just simplify it to be 2 times x plus 3, just the mathematical simplification. Also, we want to have the minimal number of states in my TEG. Right here, for example, I have 1, 2, 3, 4 states in my TEG. I don't want my TEG to have this state explosion problem. So I'm going to minimize as much as I could the number of states that are present in my temporal execution graph. How am I going to do that is by, whenever I'm creating, whenever I'm exploring the TEG, basically I come up with some new path condition, and I'm about to generate a new state, I'm going to look back in my TEG, which the state pool that I've already generated, the set of states, and I want to see if there is any symbolically equivalent state that I've already generated. If so, I will not generate a new one. I will just redirect my edge, which is now being created, towards that state. Otherwise, I will create a new state. Something to notice here that I said symbolically equivalent state. Remember, we're talking about symbolic variable values. We're not talking about states where variables have concrete values. So we cannot talk about equal states. They just need to be symbolically equivalent. Okay. And finally, this recursive kind of DFS-like, depth-first search-like exploration of this temporal execution graph while we are creating that graph will end ideally when we have all possible states created. But most often in practice, we just have time based on some deadline to explore up to some point. And then we'll just have to stop generating the temporal execution graph and start formal verification. So with that, we have the temporal execution graph. And we now can go ahead for the last step, which is formal verification of this temporal execution graph. Remember, this temporal execution graph is a model of the PLC program that was requested for execution on the PLC by the HMI server. And we want to see if that code or this model could violate my safety requirements of the physical system. So how these safety requirements are stated, I told you using linear temporal logic. What's linear temporal logic? Very briefly, it's a propositional language plus some temporal operators. So this just shows the grammar for it, and those temporal operators. So for example, you could say, I will show actually example, but temporal operators here, we have x, which represents next, basically the next state. We have u, which represents until. But we also have like indirect operators like general, globally, and eventually. So let's look at an example. Look at an example. The power operator may say, my safety requirement is that, I'm just making this up, that relay R1 does not open or should not open until generator G2 turns on, right? So we have to break this down first in atomic propositions, so-called. What's atomic proposition? They are basically the atomic statements which could take on just concrete value, which could take on either 0 or 1 at each time instant. So if we break this statement or safety requirement down in atomic proposition, we're going to end up having two atomic proposition. A1, relay R1 is open. A2, or second atomic proposition, generator G2 is on. So my LTL specification or requirement will be not A1 until A2, basically representing the same thing. Or second example, a safety requirement would say, or may say, output O2 cannot be on or true for 2 consecutive scan cycles. That will be represented by globally, when we have O1, then the next state represented by X should be off. Basically, I cannot have 2 true values subsequently. So now that I have this safety requirements and the TEG model generated, I can just go ahead and just formally verify whether that model could violate could violate that safety requirement. Something to note here is that for formal verifications, on each state of the generated temporal execution graph, each atomic proposition has to take on a concrete value, either true or false. We have symbolic states in our generated TEG model. So in our generated TEG model, for example, we have x equals a. And then atomic proposition is x is less than x is less than 10. So again, like in the state, we have x equals a, and atomic proposition says x less than 10. Whether or not that atomic proposition is true or false depends on the value of symbol a. So if a is 5, x less than 10 is true. If a is 15, x less than 10 is false. So we have to duplicate this state. And the first state, we have x equals a and a less than 10. So in that state, we have that atomic proposition true. In the second state, we have x equals a and a is larger than or equal to 10. So in that state, we have that atomic proposition false. So here it just shows that the same process of refining this, basically the whole thing actually. The first one shows the PLC program that we have disassembled. We have intercepted between the HMI and the PLC program. We lift it or translate it to our ILIL language that we saw. We symbolically execute that to create this temporal execution graph. Given this LTL spec in linear temporal logic, the safety requirement, we refine that graph so that you see at the bottom that atomic proposition here that simply is output is larger than 12. That's the atomic proposition. Now in the refined TEG or temporal execution graph, on each state at the bottom, now we have an actual value for A. So the first one, A is 0. The second and third one, it's 1 and 0. And the last one is A. So we just abstract that, and that will be the graph that we're going to use for formal verification. And as the last step, we formally verify if this generated model that the arrow just points at right now could violate my LTL requirement. The way to do it, it's just typical. We just use typical formal verification methods. In particular, we convert this negated LTL safety requirements to a state-based representation like Tableau, which is kind of a finite state machine you could consider. And we generate a product model of this negated safety requirement representation and our TEG, temporal execution graph. So remember, the TEG or temporal execution graph represents our PLC code. And finally, we're going to search for a path in this product model. So having a path in this product model, what does that mean? This product model is a product between TEG, which is our code basically, and a Tableau, which is a negated LTL safety requirement, which is basically unsafety requirement, right? So having a path in that product model, it means my TEG satisfies negated version of the safety requirement, which means my TEG violates the safety requirements. And once we have that path, we're just going to generate concrete input vectors that are real, actual, not symbolic anymore, rather than having I superindex 0, which is the input value for before the first scan cycles, and I superindex 1 and I superindex 2, we're going to have concrete values, 10 to 12. Create those that makes the program go through that path that we just found in the product model, and that basically will violate the safety requirement, and we will return this concrete value or input vector to the operator with its own, with the executable that we just intercepted right before it got, it wanted to go for execution on the PLC so that the operator could just go ahead and use the debugger to debug the program or say, hey, stop, that was not the PLC controller program that I want to upload or wanted to upload on the PLC, and which was the case in the Stuxnet case. So that kind of completes our different parts of the solution. But here, let's look at how the demo that we had at the beginning, the attack, that we showed demo of, how our solution would just detect and stop that particular attack. So here is the disassembly. Right, we are now sitting at, let me also clarify that here. Here we're sitting within the TSV device. So we have just intercepted the PLC program that has been requested by the PLC coming from, for example, let's say left, to go for execution on the PLC on my right. So I'm right on the bump in the wire device. I just intercept and disassemble that executable, the MC7 code, and that is my source code. And I want to see whether or not, let me just run. Whether or not this source code, again, just, that's fine. Whether or not that source code is going to violate my safety requirement. And this is the safety requirement that we just saw. Basically, that x10, that is one variable. This is my output wire. This is the way it is represented in our, basically in TSV. That is the the fifth, that's fine. That's an output wire that the safety requirement says globally, if we have A, my next state, the atomic proposition A, cannot be true. So we shouldn't have two consecutive true values for that output value, output variable. So the first step is just to go ahead and lift or translate the source code in instruction list language to our ILIL, the program where all the control flow are now explicit. This shows that the same program in ILIL language, as you see again, size increases significantly. The second step to run the symbolic execution on that ILIL program, as we saw. And that symbolic execution will start with some declaration of variables at the top, as you see here. And because we didn't have any control, any branch, so that asserts to true. Usually we have a lot of path predicates. And the last is the same LTL requirement or the safety requirement that we just talked about, no consecutive states with atomic proposition being true. Next, we're just going to go ahead and run the formal verification. We generate the temporal execution graph. We translate some models, and finally, we go ahead and do formal verification. That one says, right there is the formal verification output. In particular there, it's kind of hard to read, but that's a state trace within the tag or temporal execution graph that shows the path which was found, which shows the violating path of the safety requirements. This is the generated temporal execution graph. We have states. We have each state ID is the state notion is state ID plus concrete value for the atomic proposition, and labels are, the transitions are labeled by the path predicates. Right there, we have in that, that violating state there says S0, S1, S7, S6, and S4, and we see in S7 and S6 the atomic proposition getting true value, which is basically violating our safety requirement. So that was kind of how TSV would detect that simple attack that we show at the beginning. But let's see how TSV could detect kind of real PLC programs running like Siemens PLC programs. So we have larger than 30K lines of code in C and C++, and we ran on both Raspberry Pi and a desktop machine on 5 real Siemens PLC programs. This just shows the temporal execution graph that we already saw a sample of, but just here we have 2 atomic propositions. You see at the bottom of each state, we have atomic proposition A and B assigned with their concrete values, whether 0 or 1. So how large my temporal execution graph gets in actual systems, when we are exploring 14 horizon, when we are creating the tag, it'll take me over, the tag, we're going to have around 7,000 number of states when we are exploring 14 times within the horizon. How long my model checking will take? When I, again, explore 14 times in the future, 14 horizons in the future, on a Raspberry Pi, it takes right below 100 seconds, below 2 minutes. And on a desktop machine, it takes below 10 seconds. So this one shows how long each step of our processes take. So, so each bunch or group shows, the first one shows, for example, the IL to ILIL lifting or translation, and the symbolic execution, and the initial model creation, and temporal execution graph generation, and finally we have the formal verification. And each color shows a test case, a PLC program, and as we see, the most time-consuming step in this verification is the generation of temporal execution graph, which takes around 2 minutes. So the power operator will have to wait for 2 minutes to get a response back whether that code could be malicious or not. but again, running on a Raspberry Pi. So with that, I'd like to appreciate our collaborators at the Penn State University, basically my home university, and the Power World, and our sponsors, which supported different aspects of this project. So particularly what we introduced was TSC, which is a minimal trusted computing base for real-time cyber-physical malicious control malware detection, or the code injection, basically, using different three main steps. First, the lifting of instruction list to ILIL, symbolic execution of it to create a model of the program, and then formal just model checking to verify whether that code could be malicious or not. And with that, I'll just stop. Thank you so much for your attention. I'll be happy to take any questions.
Okay, does anybody have a quick question? Because I don't think we have a lot of, how much time do we have? -2, all right. Okay, I'll ask you offline.
Sure,
Okay,
definitely.
all right. Well, thank you all for attending, and be sure to attend our webinar next month. If you're on the online, you should get an announcement of the speaker and the subject. Thank you.
Thank you. Sorry, it took long.